Hi and welcome to Jaud's Academy. Today's lesson is about derivatives of trigonometric functions. But today we're only dealing with sine theta. So the derivative of sine theta is cos theta. And the derivative of theta itself is 1, and that's why I wrote right here beside the cos theta 1, because of not only taking the derivative of trigonometric function, also we have to consider the derivative of theta itself too. So in this case, the coefficient of theta was 1, so the derivative of 1 theta would be 1. All right, now, you know by now the derivative of sine theta is cos theta. But what's the reason behind it that the derivative of sine theta is cos theta? Because we must understand the reason to why the derivative of sine theta is cos theta. Not just memorizing because someone told us the derivative of sine theta is cos theta. But you have to have an argument to why the derivative of sine theta is cos theta. And here I drew the graph of sine theta, and I want to show you exactly why the derivative of sine theta is cos theta. So this is the graph of sine theta right here. In order to find an expression for derivative of sine theta, we find the slope between any turning point and a turning point, the instantaneous rate of change, or the slope of a tangent to the curve, right, in order to find the derivative. So I would pick points in order to find or draw the tangent, the tangent line between any two turning point and a turning point, where the slope of a tangent changes its directions. So between this two turning point, I can pick a point right here and I draw my slope of a tangent. And then I can pick a point right here, draw my slope of a tangent right at turning point. And between the two turning points also, I'll pick a point right here and I draw my slope of a tangent. And a turning point right there, I draw my slope of a tangent. And between this and that, I'll draw another slope of a tangent that touches the curve at one point. And then now we go ahead and determine exactly what the slope of these tangents are. Since it increases the slope of a tangent at this point, so if it increases, meaning that it's positive, so it will be above the x-axis. So we have a point somewhere right here above the x-axis. The slope of a tangent of this would be positive. That's why we have a point above the x-axis. Now, the slope of a tangent that is horizontal, you know that slope of horizontal is 0. So it's right across, right on the x-axis. So the slope of a tangent to this point right here, a turning point, would be 0. So we have a point right on the x-axis. Now, the slope of this, at this point, the slope of a tangent is negative since it decreases. So we have a point below the x-axis. So anywhere below the x-axis. Now, in here, at turning point, again, the slope of a tangent is 0. So we have a point right on the x-axis. And the last one, the slope of a tangent here would be positive. So we have a point above the x-axis. Anywhere above the x-axis. Now, to connect these points, and you can see it has a shape of cosine. Now that's the reason why the derivative of sine is cos. Let's do another example. I earlier mentioned that we don't forget to also consider not the derivative of function itself, the theta also. So here's another example. We have y equals sine 2x or sine 2 theta. X represents 2x represents the theta for sine function here. So now, to find the derivative of sine theta itself, we said the derivative of sine theta is cos theta. And now don't forget to take the derivative of theta, multiply outside by cos theta. And the derivative of theta would be the derivative of 2x is 2. So therefore, to put it in simplest form, we have 2 cos theta. So this is what I mean. You have to be careful not only taking the derivative of the function, but also the derivative of theta. Let's do another example here where we do chain rule in terms of trigonometric function sine theta. And right here, this is another nice example which clarify everything in terms of derivative of sine functions. So you can see that we have sine to the power of 2 and theta. I can rewrite this as also sine theta all to the power of 2, because I want you to recognize this is a chain rule types of derivatives. So in order to apply chain rule to find an expression for slope of a tangent or finding the derivative of this expression, we go from outside to inside. So starting from the power and then inside the derivative inside the bracket. So to do that, so y prime or dy by dx would equal to the exponent multiplied by the coefficient of the bracket, which is 2, and then we reduce by 1 degree the exponent by subtracting by 1, so it'd be 1. So we have sine 2x sine theta. Now we take the derivative of inside the bracket, which is sine theta. We said the derivative of sine theta is cos theta. Then we go really in deeper to find the derivative of theta. Now don't forget to find the derivative of theta also, that multiplies outside right here. So the derivative of theta is 2. Now to put it in simplest form, we have 2 times 2 would be 4. And we have sine 2x and cos 2x. So the answer is in simplest form right here. Y prime equals 4 sine 2 theta cos 2 theta. So we went from outside to inside and to inside. So we took the derivative of the power, multiplying by the coefficient, subtract 1 from the exponent, and the derivative of inside multiplies by the outside, and also the derivative of theta, don't forget, multiplied by all the way outside right here. And then you can simplify. And that would be the derivative of this trigonometric function using chain rule. All right, so I'm just going to stop right here. I'm hoping that you enjoyed this video clip and understood the concept of finding the derivative of sine function, and I'll be doing more examples and more video clips about other trigonometric functions, so please do watch those videos. And so please don't forget to subscribe. If you have any concern or questions, leave it below in the comment box. I should be able to get back to you as soon as I can. And other than that, good luck. Wish you all the very best.